Namaste. In this lecture, we shall explore sustainable development case discussions. By working through real-world cases, we will practice applying the concepts from earlier lectures this week rather than treating them as abstract ideas. Cases help us see how ecological, social, and economic considerations interact when actual decisions are made. Before we enter the first case, let us establish a shared framework. It has 4 questions. First, what development goal is being pursued? Housing, food, transport, energy, or income? Naming it clearly prevents confusion later. Second, what ecological system is affected? Third, who benefits and who bears the costs? Benefits and burdens are rarely shared equally. Fourth, what happens in the long term? Decisions that look attractive in the short term often produce serious ecological or social costs many years later. Keeping these 4 questions in mind will help us read every situation more completely. Now let us add the analytical lens from this week. For each case, we will examine the environmental pillar, that is ecological integrity, the social pillar, fairness and well-being, and the economic pillar, long-term viability. But biodiversity must remain consistently visible across all the 3 pillars. It is not a separate topic added at the end. Biodiversity supports ecosystem services, maintains resilience, and influences what kinds of development are actually sustainable over time. So biodiversity should appear throughout the analysis, not only as a final environmental footnote. Before we begin, one more important point. Sustainability cases rarely have a single correct answer. Many involve genuine trade-offs. Good analysis does not pretend that conflicts are absent. Instead, it makes those trade-offs visible, it reveals hidden ecological dependence, and it clarifies what different pathways will likely lead to. Better decisions usually begin with better questions. So we should approach each case not to deliver a verdict, but to develop the habit of looking at the full picture. Our first case is forests and livelihoods. Forests are classic sustainability examples because they are multifunctional. They may provide timber, fuel wood, food, medicinal resources, and income. At the same time, they regulate water, influence local climate, store carbon, and support biodiversity. Many local communities depend on forests directly, while wider societies depend on forest services indirectly through water and food security, among others. Forest decisions are therefore simultaneously about ecology, livelihoods, infrastructure, and long-term risk. Any analysis that treats a forest as only one of these things will miss important parts of the picture. A forest can be seen in very different ways. One view treats it mainly as an extractable resource, timber and products to be harvested. Another treats it as ecological infrastructure that regulates water, climate, soil, and biodiversity. A third treats it as a livelihood base for communities who depend on it culturally and economically. Sustainable development requires integrating all these 3 views. When only one perspective dominates, other values tend to be lost, without anyone explicitly deciding to lose them. The sustainability questions for a forest case are therefore these. Is extraction within regenerative limits? Are biodiversity and ecosystem functions maintained? Are local livelihoods respected, or are benefits flowing away from those who have historically depended on the forest? And are long-term services like water regulation being undervalued because they do not appear clearly in account statements. These questions prevent a shallow reading and push toward a more complete assessment. If forest decisions are made too narrowly, several hidden costs tend to emerge over time. Water systems can become unstable, soil erosion can increase, biodiversity may decline, reducing the resilience of the whole landscape. Local income security can weaken if direct users lose access, while short-term extraction benefits flow elsewhere. And overall resilience may fall, making the system more vulnerable to disturbance. Many of these costs do not appear immediately, which is why unsustainable forest management can persist. It looks profitable for years before the underlying ecological capital visibly deteriorates. Recognizing this delay is an important part of reading forest cases accurately. This slide asks us to practice reading a forest as a system rather than as a stock of wood. A forested landscape holds water pathways, soil structure, habitat for a wide range of species, climate regulating function, and livelihood connections for nearby communities. When we train ourselves to see forests in this way, the ecological and human stakes of forest decisions become much clearer. A more sustainable pathway in forest management typically involves several connected elements. Limits-based harvesting, set at rates that the forest can regenerate. Protection of high biodiversity and ecologically sensitive areas. Meaningful inclusion of local communities in governance and decision making. And valuation that includes ecosystem services alongside products. Sustainable forest management does not mean that all usage should stop. It means use must be designed around ecological regeneration and social fairness rather than driven purely by short-term extraction. Our second case is wetlands and urban expansion. Wetlands are especially vulnerable because they are frequently misread. In a narrow economic view, they can appear to be unused, unproductive spaces that are waiting to be converted. But ecologically, they are often highly functional, storing and releasing water, buffering floods, filtering pollutants, supporting biodiversity, and connecting hydrological systems. When cities expand into wetlands, the immediate gain is buildable land, but the long-term ecological loss can be far greater than the short-term gain actually suggests. Wetlands face intense pressure because urban land demand is high and their ecological value is less visible than their potential market value. A parcel of land can be priced very easily, but flood buffering and habitat support are much harder to express in monetary terms in advance. And this creates a systematic bias. The benefits of conversion are immediate, they are obvious, while the costs are delayed and distributed across a wide population. Sustainability analysis therefore exists partly to correct this bias by making the full picture visible before the decision is made. The key questions here are practical. What service is lost if the wetland is filled? What future flood or water quality costs may follow? What biodiversity is affected? And are alternatives available? Directing growth to lower function land or redesigning the expansion to leave the wetland intact? Sustainable development is not simply about allowing or stopping the development. It is about asking whether development is being designed wisely or not. The distributional question is also very clear here. Downstream communities may face higher flood risk. Low-income neighborhoods, often in lower lying areas, may be especially exposed. Water users may face higher treatment costs. Local biodiversity loses its habitat. Future city budgets may carry the burden of expensive engineered drainage that tries to replace what the wetland was once doing for free. And this case shows directly how ecological loss becomes social and economic loss over time, and how resources are taken away from many and put into the hands of a selected few. The key conceptual shift here is to see a wetland not as an empty space, but as a natural infrastructure. Infrastructure is the category we use for what a city depends on: flood protection levees, drains, water and waste treatment systems, and so on. A functioning wetland performs several of those functions simultaneously. It stores water, so it's a storage structure. It slows the peak flows, so it's a flood protection structure. It filters contaminants, so it's a water treatment structure, and it supports habitat. Once we see wetlands in this way, filling one becomes clearly a trade-off with long-term infrastructure consequences, not simply a decision about an empty area. A more sustainable pathway would involve avoiding the highest function wetland areas during the planning stage itself, using probably zoning and protective buffers, integrating green infrastructure into cities design, and evaluating long-term risk rather than only the current land price. Urban development works better when it is designed around the hydrological reality of the area. Attempting to erase that reality and pay the cost later is both economically expensive and ecologically damaging. Our third case is agriculture and biodiversity. The relationship between them is more complex than simple competition, because agriculture depends on soils, water, pollinators, natural pest regulation, and landscape stability. All of these are ecological relationships. Intensification can increase output in the short term, but if it simplifies the ecosystems too aggressively, it may reduce biodiversity and increase the vulnerability of the productive system itself. Agriculture is therefore one of the clearest cases for understanding both synergy and trade-off within sustainability. The narrow view of agriculture focuses almost entirely on maximizing the seasonal output. It simplifies landscapes by removing non-crop habitat, reduces diversity for efficiency purposes, and treats biodiversity as separate from production. And this can sometimes increase output in the short term, but it often builds fragility into the system without even recognizing it, because the ecological support functions removed do not immediately produce a visible crisis right at that point of time. The sustainability view asks a broader question: not just how much is produced this season, but what makes sustained production possible over time. Let us think through a few specific pathways. Repeated chemical inputs can alter soil pH or salt levels, gradually degrading the very medium crops depend on. Excess fertilizer washing off the fields can trigger eutrophication in nearby water bodies, where nutrient overload causes algal blooms that deplete oxygen, damaging aquatic life and the water supply that neighboring communities themselves rely on. Pesticide use at high intensities can harm pollinators that nearby fruit groves or honey farms depend on, weakening both ecological function and rural livelihoods. And a portion of these chemicals inevitably enters the food chain itself, affecting the very communities that consume produce from that area. Biodiversity in this view is not a separate concern, therefore. It is part of what keeps these harms in check through natural pest control, pollination, bioremediation of chemicals, and soil health. These pathways lead directly to the right questions for an agricultural case. Are soils and water being degraded through chemical inputs? Are pollinators and other supporting species being lost in ways that will reduce yields and harm neighboring livelihoods over time? Are the communities consuming this produce being exposed to accumulating chemical loads? And more broadly, is current output being sustained by ecological function or by practices that are quietly undermining the future system? Sustainability analysis here requires us to look beyond the field boundary and ask what is happening to the soil, the water, the pollinators, and the people themselves who are connected to this landscape. Having identified those risks, we should also recognize that sustainability in agriculture is not only about restriction. There are real synergies available. Habitat strips and field margins can support the beneficial insects and pollinators that intensive zones have lost, so we can compensate for them. Reduced pesticide application, guided by ecological understanding, can protect the pollinator networks that nearby farms and orchards depend on. Soil conservation practices can help restore the pH balance and reduce chemical dependency over time. And these approaches do not simply limit production. In many cases, they stabilize it, they sustain it. And that is the core insight. Agriculture tends to be more productive and more resilient over time when it works with ecological processes rather than against them. This visual reminder reinforces that even intensively farmed areas contain or could contain ecological relationships. Trees within and around farms, margins around the field edges, and small water bodies can influence the landscape resilience and ecosystem services. The point is to see agriculture as embedded within a broader ecological system, not as a domain entirely separate from nature. Our fourth case is mangroves, coasts, and development. Coastal zones attract intense development pressure from tourism, settlement, and production. Mangroves provide shoreline protection by absorbing wave energy. They also provide a nursery habitat for many fish species. They are carbon storage structures and they also provide biodiversity support. So, this is a strong case where biodiversity conservation and risk reduction point in the same direction. When mangroves are removed, the costs often do not appear immediately, but can become severe, particularly during coastal storm events. The short-term versus long-term contrast is very visible here. Immediate gains may come from converting mangrove areas to tourism facilities or to aquaculture ponds, but coastal resilience may decline in the process. Fisheries that depended on mangrove nursery habitat may weaken, and disaster exposure may increase as the natural buffer disappears. The costs are typically borne by communities who live on the coast, while the benefits are often captured by developers or industries who do not remain there permanently. The image on this slide shows an earth mover constructing gabion rock check dams along a coastline where mangroves are absent. This machine, this rock, this engineered wall, all of it exists because a living system that once did this work for free is no longer there. The nursery habitat that sustained fish populations is gone. The roots that held soil against tidal energy are gone. The wave buffering that the mangrove forest provided quietly, continuously, and without an invoice must now be purchased from a contractor and purchased again when the structure corrodes, shifts under storm load, and needs repair, reinforcement, and eventual replacement. This is where the structural incentive problem becomes visible. Every cycle of construction and repair is a contract to be awarded and a budget to be spent. When the people who make recommendations about coastal land use are also the people who stand to gain from construction activity, the economic logic quietly favors removal of mangroves over conservation, regardless of what the ecology actually requires. But it is not the contractors who pay when the arrangement unravels. The taxpayer pays first and most quietly, funding every round of construction, repair, and replacement from the public exchequer, with no say whatsoever in whether a free ecological alternative was ever seriously considered. The fishing community pays next, in disappearing catches, in livelihoods that took generations to build and can be lost in a single bad season. And there is another cost that rarely appears in the initial accounting: the loss of tourism. People travel to experience mangrove forests, to see the biodiversity, to walk the waterways, to encounter and marvel at a living system. That tourism generates income for local guides, boat operators, homestays, and small businesses, with multiplier effects that ripple through the local economy. No one books a trip to see a concrete seawall. When the mangroves go, the entire stream of ecological tourism revenue goes with them. The broader coastal community then pays further still in flood risk, in damaged homes, in a shoreline that was once both a source of income and a place of belonging. And when the engineered structure finally fails under a storm it was not built to survive, everyone pays again, in emergency response, in reconstruction, in grief, while those who gained from the construction contracts have long since moved on to the next project. It is the people who remained, the ones with the least say in the original decision, who are left standing in the damage. And this is what the unequal distribution of ecological loss looks like in practice: benefits flowing to those with access and influence, and costs falling on those who had neither. Our fifth case is urban green spaces and livability. Cities are ecological spaces too. Urban green spaces regulate temperature, support mental well being, improve air quality, help manage stormwater, and provide habitat for many species. Urban biodiversity may be less visible than biodiversity in forests, but it still matters to sustainability and to the daily quality of life. Including a city case is important because we sometimes assume that biodiversity and sustainability apply only to remote natural systems. The planning tension in cities is real. More construction can reduce green cover. Less green cover can increase urban heat stress. What appears land efficient in the short term may reduce long-term livability. There is also an equity dimension. Access to urban green space is often unevenly distributed, with lower income areas having less. Decisions about green space are therefore social sustainability decisions as much as they are environmental ones. Does the city design with ecology or against it? Are urban green spaces treated as decoration or as essential infrastructure for livability? Who gains access to cooling, recreational, and health benefits? And what biodiversity can the city still support through thoughtful planning and green corridor design? This case reminds us that sustainability thinking should shape ordinary urban planning decisions, not only protected area policy or rural land management. You now have the framework, so let us try applying it here. Think about a city you know. What are its green spaces and who has access to them? What happens to heat, water, and air quality as green cover is reduced? Who gains when land is converted from a park or a pond to a building? And who bears the cost? What recreational value is lost? And what local economic activity goes with it? And when an aging resident or a young child loses access to the only green space in the neighborhood, what kind of loss is that? Is it environmental, social, economic, or a combination of all these? Work through these carefully because the urban case carries every pattern we have seen in this lecture, just in a setting that is closer to where most people actually live today. Now that we have moved through all 5 cases, we can ask what they share. 4 patterns emerge. Short-term gains can hide long-term losses across every sector. Ecological services are consistently undervalued because they are difficult to price in advance. Biodiversity is linked to system reliability, not merely to conservation ethics. And the costs and benefits are unevenly distributed. Sustainability analysis must always ask who gains and who pays. We should carry away one important nuance. Trade-offs are real, and we should not pretend otherwise. But not all trade-offs are equally unavoidable. Some arise because planning was too narrow and better design was available but not considered. Some shrink when ecological services are properly valued, and some involve losses that are genuinely difficult or impossible to reverse, such as species extinction or permanent soil degradation. Strong sustainability tries to minimize irreversible ecological losses, rather than assuming that everything can be eventually replaced or repaired. Biodiversity appeared in every case we examined, and this is not coincidental. Biodiversity reflects the condition of ecological systems. It supports the ecosystem services that human activities depend on. It contributes to resilience by maintaining the variety of species and functions that help systems recover from disturbance. And declining biodiversity often provides early warning of deeper ecological stresses before those stresses become a visible crisis, a signal that is hard to read in any other way. And that is why biodiversity belongs at the center of sustainable development analysis, not at its margins. Connecting back to what we explored on indicators earlier this week, we can ask what measurements would actually help us track outcomes in these cases. Habitat quality and extent matter across all of them. Water or soil condition is relevant dependent on the case. Biodiversity trends over time are also essential. Livelihood and equity measures help reveal social outcomes that purely ecological data might miss. And long-term risk indicators such as flood frequency or heat stress intensity matter, especially in wetland, coastal, and urban cases. Good sustainability judgment is always supported by good measurement. It is useful to recognize what weak sustainability analysis also looks like. A weak analysis focuses on one benefit only, usually the most visible economic gain. It ignores ecosystem services, it forgets to ask who bears the losses, and it assumes that any ecological damage can be repaired easily later. That last assumption is especially dangerous because restoration is often expensive, slow, and incomplete. Degraded soils, filled wetlands, and locally lost species cannot always be recovered, even with significant investment. A stronger analysis compares short-term and long-term outcomes deliberately. It includes ecological function and biodiversity as integral parts rather than optional additions, and asks clearly who benefits and who pays, and looks for redesign options before jumping to simple approval or rejection. This is a practical sustainability mindset. It aims to improve the quality of decisions by widening the frame of analysis, not to prevent development, but to make development better. If today's lecture is reduced to one line, it is this: sustainable development means reading development through ecological, social, and long-term consequences. That statement explains why case discussions matter. Real situations are always more complex than definitions suggest, and cases train us to see beyond immediate, visible gain and toward the wider system in which every development decision actually happens. Let us gather the key terms from this week. Sustainable development gives the overall direction. The three pillars organize the analysis. Ecosystem services make visible the ways ecological systems support human activities. Biodiversity helps explain system function, resilience, and the early warning signals of ecological stress. Indicators support rigorous assessment. Ecological boundaries remind us that natural systems have real limits. And trade-offs and synergies describe the kinds of choices that appear in every realistic case. These terms now carry meaning through the cases we have examined together, not only through their definitions. For revision, you should work through 4 levels of understanding. You should be able to define sustainable development case discussions and explain what this kind of analysis is for. You should be able to distinguish this approach from narrower economic or purely ecological analysis. You should be able to explain the main patterns: hidden costs, uneven distribution, ecological dependence, and the importance of long-term thinking. And you should be able to apply this approach to a new case, connecting sustainability reasoning to biodiversity conservation and real-world decision-making. In the coming week, the course shifts from the sustainability framing we have developed to the direct pressures that threaten biodiversity. We move from examining how development decisions interact with ecological systems to understanding the major drivers of biodiversity loss itself. The analytical habits built this week will remain relevant as we examine those pressures. Before we close, take a moment to reflect. How can the ideas discussed today help us understand or solve a real sustainability challenge? As you think about this, try to connect the framework from today: the 4 questions, the 3 pillars, the role of biodiversity, to a specific local environment, a policy decision, or a livelihood community that you are aware of. The strongest responses will move beyond general statements and identify a concrete situation where this approach actually changes how we read the case. And that is all for today. Thank you for your attention. Jai Hind.